So, yesterday we looked at different kinds of fuel cells that exist or that has been designed where you can use hydrogen or a hydrocarbon based fuel and convert the using a catalytic properties of the electrode, so you can convert your chemical energy into electrical energy. And we saw like the different kinds of fuel cells have, so mostly they all have a platinum electrode, or some can have a nickel electrode as well. Mostly this solid oxide fuel cells, so which are operating at very high temperature, about 1000 degrees Celsius, and therefore uh, there are several challenges with many of these or most of these fuel cells for practical applications. I mean, one is of course concerning how you can get the fuel, hydrogen fuel, efficiently and a clean fuel which you can store. So that is about the infrastructure what you can get uh, for the fuel. However, one can also improve the efficiency of these fuel cells as well, and nanotechnology or nanomaterials are really going to play an important role here as well. So we addressed several challenges also, like uh, just to review that. So is high cost of the electrode material because platinum is used, which has like one of the best catalytic properties so far amongst. So it is a noble metal, and it also does not react or participate in the chemical reaction, although it is one of the best catalyst. And so we will see how these challenges can be addressed using nanotechnology. So high cost of the electrode material, as well as its durability or uh, its performance should not degrade when it is in continuous operation. So the best strategy so far when we are talking about this nanomaterials means, so we have a bulk electrode, and instead of taking a bulk electrode, so can we make can the electrode be made from this nano-sized materials, for example nanoparticles. So that will definitely help, as you can see that when we are going to nano-sized particles or nanoparticles, so we increase the surface area, and what has been observed is this catalysis or this dissociation, adsorption, all this happens mostly on the surface of the material. So therefore, if you can take nanoparticles where the number of surface area is high, or the surface to volume ratio is high, so that means you can increase the catalytic property of the material. So that is a very simple strategy to adopt, and that has indeed been adopted, and people have used various kinds of, so mostly again platinum nanoparticles has been used, so during using various chemical synthesis processes. And it has also been observed that you can reduce the cost as well as you can increase the efficiency as well. However, this in when we talk about this catalytic properties of the surface, so it has been observed that all surfaces are not really active acting as an active site for catalysis. So so these materials are like they have crystallographic planes like we saw, so 100, 111, so different planes they have, and different planes have different catalytic properties. And why it is so? So depending on what so mostly this catalytic property means uh, your your gaseous particle which is going to be reduced or oxidized, so hydrogen or oxygen, they should get adsorbed easily, okay, and then they should dissociate, and then they should dissolve also. That should not be difficult to dissolve as well. So if they dissociate and stick on the surface, or form a chemical bond which is much stronger and don't dissolve easily, so then uh, and don't move into the electrolyte, so it is not helping in terms of efficiency. So therefore, you need surfaces which can adsorb easily, so the energy barrier is low for adsorption, as well as it will dissociate quickly and then move or diffuse uh, from the surface. And in that sense, all the surfaces of platinum, for example, are not really the best surface to have a catalytic behavior. And in that sense, nanostructuring has helped quite a lot, where people are designing uh, morphology with those surfaces which are really active or which are responsive for catalytic properties. So that means those surfaces which are really good for catalysis, so you can create nanomaterials or nanostructure in such a way that those surfaces are only exposed to the incoming hydrogen or oxygen, so that your oxidation or reduction can happen. So this is uh, like different designs which have been actually possible in case of platinum nanoparticles. So these are all platinum nanoparticles with different shapes. So as you can see, so different shapes have different surfaces which are exposed and which can be used for catalysis. Uh, And what was actually observed is that if you look at the platinum 100 substrate, so like in case of the cube, so you have the 100 surface which is exposed. So that surface has much better catalytic property. Okay, so that has a better catalytic properties than 111 surface. And mostly the surfaces, which surfaces are mostly responsive or the best for catalysis, the surfaces which have less number of or more number of defects or steps or kinks in their surfaces. So that means uh, the number of defects are more, then those surfaces actually are better for catalysis. Okay, so they have more number of dangling bonds, so that is why they are good for adsorbing these fuel and dissociating it. And in case of platinum, it was observed that platinum 10 surface is much better compared to platinum 111 surface, and therefore people started using. So in the beginning, mostly spherical nanoparticles were used, but later on, uh, as people understood which surfaces are better for catalysis, so then this cube shaped nanoparticle were preferred, and compared to any other anisotropic shape like octahedron shape or spherical nanoparticle. So using cube shaped nanoparticle, one can increase the catalytic properties of the nanomaterial, of the electrode material. So there are other advantages with using these nanoparticles. So one obvious reason is so you can reduce the total weight of the electrode. So in the bulk form, so you are taking so maybe few centimeter of the bulk electrode material, and mostly the surface, the catalysis is happening on the surface, and most of the platinum material remains unused, and it is kind of like wastage of material, which is they are not participating in the catalysis. However, you need it, so that I mean it will always be there. But when you replace with these nanoparticles, so now you can take less number of platinum, the material, the total weight of platinum that you need. Okay, so that is reduced. Okay, and that is how you can reduce even the cost of the electrode material. So typical size is like around, like you use normally some clusters, so 10 nanometers, so 5 to 10 nanometer in that range. Uh, but another problem with using this nanoparticle is, since they're so small and reactive, so sometimes you need to passivate it. Otherwise, what will happen? These clusters will form. Uh, they will agglomerate. Okay, so they since the surfaces are highly reactive, so these and they always try to minimize the surface energy, so therefore they will agglomerate, and which is undesirable. But you cannot passivate the surface, because once you passivate, then you also lose the catalytic property of the surface. And that is actually a big bottleneck in platinum nanoparticle as well. So this agglomeration uh, can hamper the catalytic behavior of the electrode. And therefore, people thought of using wires and rods. So, this extended versions. So, instead of taking nanoparticles, so these nano wires or nano rods, they have extended surfaces. However, they are not so they don't agglomerate so quickly, so you can expose so you can put these nano wires or rods instead of nanoparticles, so you still can use the surface catalytic properties without agglomeration. And in the so in the beginning nanoparticles were used, and later on this nano wire or nano rod, these structures were actually used quite a lot. So that means this 1D structures give better stability, or less agglomerate less compared to your 0D structures. And this is example of this nanowire, one particular kind of nanowire which was used for catalytic properties, and which showed very impressive catalytic behavior. Uh, so these are mostly platinum with alloyed with. So in this case, the example shows platinum nickel nanowires, and what you see is that the green is your nickel. So maybe I should put it in green. Yeah. Okay. So this is your nickel, and on the surface what you see is this red one is your platinum. So you take a nickel nanowire and coat it with platinum. So this is actually not a coating, but rather it is a platinum nickel alloy that you make. And what was observed, that if you take this uh, platinum and M, where M stands for cobalt or nickel. So these are really good for catalytic behavior. And in this case, you can again, what you observe is you can reduce the amount of platinum that is needed for a catalytic behavior. So you get the same performance, or you can improve the performance even using less platinum. And so you can again reduce the cost. So these are different strategies how you can achieve or reduce the cost of your fuel cell, as well as you can improve its performance. And then also another strategy is people started using this nanoporous or hollow structures or core cell. So they prepare this core cell structure, and then using this core cell, so you can prepare hollow nanoparticles. So this is an example here. So where a core cell structure is used, this is silver core and platinum shell, and then they used some etching technique. So mostly this acetic acid and in oxygen atmosphere. So you can etch differentially the core, the silver, and what remains is you make a hollow nanostructure with platinum, and maybe this during this etching process some of the uh, silver nanoparticle diffuse into the lattice of platinum and they remain there, and this is what you get, a hollow structure. And again, since you are using this hollow nanostructures, so what you have is you are exposing more surface area for, and more surface area is available for catalysis. So in the, even in the nanoparticle, so sometimes it is anchored on a substrate, so that part will not be used, and maybe only part of the surface will be used. Now if you make it hollow, even more surface area is available for catalysis, and that's why you can even reduce so you can increase the efficiency, because you can increase the number of like the sites where catalysis can happen, so you can increase that, and that is also a advantageous, and people also started using this hollow nanostructures as well. And what in these examples, like for example, we have the silver and platinum, or this platinum, cobalt, or nickel alloys. What you clearly see is platinum is not actually used alone as electrode material. It is either alloyed with something or mixed with some other material, uh, which helps in the catalytic properties. And this is also quite interesting, and a lot of effort or research is still going on to understand what roles actually these materials, I mean, why platinum alone is not showing a better catalytic properties compared to this alloy. So this is again a very active field of research right now. So lots of open questions still remain, like what kind of uh, electronic transfer happens. So how this adsorption and dissociation, and as well as this desorption happens on these core cell or on these uh, alloyed nanoparticles or nanostructures, that leads to a better catalytic behavior. So oxidation and reduction reactions. So normally, so in this fuel cells, what is always happening is a oxidation and a reduction. Okay, so this reactions, that chemical reactions is happening. So what is the reason why this this is better on this chemically alloy rather than just pure platinum nanoparticles? Okay, so another thing what you also see here is or realized is that, or even even that is necessary, is that when you are using this platinum nanoparticles or nanostructures, so you have to support it on some substrate, right? I mean, on some material. If you do not use a supporting material, so just platinum nanoparticle itself will not will not be structurally stable. So you need actually a like a backbone or a structure on which these nanoparticles will go and sit and then do their job, which is which is catalyzing or reducing or oxidizing your fuel. And so in that context, a lot of people started using different support materials. So you need support materials for these noble metals, or this even this. So you want to support your nanowires or nanorods or nanoparticles on some material which is structurally stable. And now then people started exploring actually carbon nanostructures. That is like right now one of the biggest or like the active research area where carbon nanostructures are actually used as support material for these noble nanoparticle for catalysis. Uh, so you can make again in carbon nanostructures we saw carbon nanotubes can be used or graphene can be used. So these are all alternatives that exist which can be used as support material for your uh, nanoparticle. And mostly nowadays, of course, graphene is extensively being researched. Uh, I mean, one of the reason is these carbon nanostructures provide some kind of defect surfaces. If they have some defects, so that can also enhance the catalytic property of the electrode. And then, of course, it will carbon-based materials will make the electrode lighter, and again, graphene and carbon nanotubes, their mechanical properties is really excellent. So good mechanical strength, so they can also retain their stability or structural stability even for longer duration of during longer operation. So this durability will also be there, and therefore these carbon-based structures are actively now being used for support material. Yeah, this is just an example of how this graphene is used as a support for these nanomaterials for catalysis purposes. Although graphene is not actively participating in catalysis, but it is helping or supporting these nanoparticles which act as center for catalysis. In fact, while people were using this carbon-based structures, so they thought, can we replace this platinum altogether, these noble metals like platinum or nickel, for example, completely, so that the cost will be even can be reduced further. So then, and again, graphene was kind of a material of choice because it was acting as a used as a support material. And then people started doping with nitrogen, sulfur, and they made even different morphologies or different structures with graphene as well, which showed a better, yeah, somewhat better catalytic properties, but still it is kind of at a beginning stage, and clearly a lot more needs to be done, which which can lead to maybe replacement of this platinum as an electrode material. And another thing which most of these nanoparticles or nanomaterials they lack right now is, so what we have shown is these nanowires, nanoparticles, or nanorods or these two-dimensional materials. Okay, so they all are still used in the lab. Okay, so that is still nobody has shown a real practical application of this a fuel cell based on these materials. And I mean, one of the reason is when you make these nanomaterials, so you use a lot of like chemistry, and the synthesis process is not trivial, and sometimes it is not reproducible, and also it may not be, you cannot scale up this fabrication processes, because for example when you are doing this hollow nanostructures, or even so some nanowires you can grow in an industrial scale, but again putting this platinum or making this alloy is always expensive as well, and most of the time the problem is it is not reproducible. So therefore most of these examples what we have seen here are all done in the labs, and it has not been really translated into a real application in a fuel cell so far. Uh, but one particular design which has shown a lot of promise probably can be used for real applications is a kind of this nanostructures which are called whiskers. Okay, so these whiskers are basically you can create it, and it has a good the probability is there it can be scaled up easily. Okay, so what is used is a nanostructure. So these are nanostructured substrate or microstructured, rather not nanostructured. These are microstructured substrates on top of which you grow these whisker-like shapes. So all in random orientation, uh, and then what you do is, what you do is on these whiskers. So they are not really acting as your active catalysis, rather these are just supporting, they are providing the support. Okay, these structures, and then you coat on top of that your material that you want to use for catalysis. For example, here they have coated this uh, platinum cobalt manganese. Okay, so this is what they have coated on this whisker, so one can take a different alloy, or depending on which one is better, also is better catalytic properties. So they used here platinum cobalt manganese in this particular example, but these structures can be used or can be scaled up for industrial applications. So because they are using a sputtering in this case, and therefore you can use it for real applications. Although this So these whisker structures you can grow by some chemical etching of the substrate, and then you can deposit your platinum alloy on it, just like a sputtering. You can coat it, and then you can use it for electrode materials. That is like probably one of the closest uh, to the real application so far of nanostructured material, or in this case it is a nanostructuring that can be used for fuel cell applications. Okay, so another problem which we really did not touch upon yet, in the context of the solid oxide fuel cells is, so we saw in solid oxide fuel cells what we have is, the working temperature is quite high, about 1000 degrees Celsius, and there one can only use few materials uh, as electrodes. So nickel based materials normally is used, and also the electrolyte, this zirconia, or zirconium oxide or yttrium oxide, that is actually used as an electrolyte there, because of this high working temperature. And now the research is being done, so how these nanomaterials can be used, which can reduce probably the working temperature without compromising on the performance of the fuel cell. What they want to make is a low temperature. So low temperature is not like below 0 degree Celsius. So in this context, in solid oxide fuel cell, low temperature means so going to like 500 degree Celsius or 600 degree Celsius. So that is the low temperature in this context. That are actually, people are trying to do that using nanomaterials. So there are various ways that can be done. So, for example, you can. So, so I should not mention the name doping here, but rather it is coating. So a palladium nanoparticle is coated on nickel anode, or sometimes this nickel gadolinium and carbon-based uh, alloy is also used instead of pure nickel, because of this high temperature applications. And with palladium nanoparticle, so it it has been observed that this solid oxide fuel cell can work even at 650 degree Celsius instead of going to 1000 degree Celsius. So you can operate the solid this fuel cell at 650 degree Celsius. And moreover, this palladium nanoparticles also protect from formation of carbon deposition on these electrodes. So when you are operating at high temperatures, what can happen is, this nickel based anode, so you I mean, if you have a pure hydrogen fuel, it is good, but it is always mixed with some other hydrocarbons, and these carbon materials can get deposited on your substrate, or on your electrode material, and which normally used to reduce the life cycle of the fuel cell. They will degrade your electrode material as well as the catalytic properties. And by putting palladium nanoparticle, so you can get rid of this carbon deposition as well. As well as, again, palladium is also, so similarly it is very similar to platinum as well. Okay, so like platinum nanoparticle is used for catalysis, palladium exactly behaves almost like the same, and it is also noble and expensive as well. So palladium normally is as expensive as platinum, it can be. Okay, so this is what people have tried in the in solid oxide fuel cell, and even they are trying to make a nanostructuring of the electrolyte material. So this electrolyte is also like a thin film form. So you can make a thin film electrolyte. So where you are using this yttria or zirconia, that is actually used in the solid oxide fuel cells. So one can use this yttria, zirconia, or a composite of that to and make it a thin film like structure, so that So of course it will the total size of the fuel cell will be reduced, the total volume will be reduced without and also the performance will not be compromised. So in that sense, this nanostructuring can also help in solid oxide fuel cells. And people are also trying to make so I did not mention here, so composites one can also make. Okay, so nanocomposites, where you can take so advantage of so what you have is in a nanocomposite you can have multiple interfaces. Okay, so these interfaces can also act as your adsorption sites and can enhance the catalytic properties as well. I mean, these are all kind of strategies which are now being explored to replace your bulk platinum electrode and reduce the cost. And also, there are also research going on in what kind of solid electrolyte one can use, or can one nanostructure this electrolyte as well. So there are various strategies that is investigated, and still, let's say in the lab, and it has not been translated into real fuel cells yet. And hopefully, in next no no 5 years or 10 years, depending on the investment from the industry, so this research can uh, I mean, this translation from the lab to the industry can happen faster. Uh, but however, these catalytic properties, I mean, this fundamental catalytic properties, how this catalysis happens on different surfaces, that is also a very interesting problem for the research community. and uh, and this is also like one of the like mostly this is done by theoretical calculations. So theoretical modeling where people look at how this, as I said in the beginning, how this desorption, adsorption, dissociation, and desorption and diffusion takes place, and how the electronic structure of different surfaces. So different surfaces, so they have atomic density, so different atomic density and defects, and that is going to affect the electronic structure. And this electronic structure, how this electronics, so that means this in the adsorption process or in dissociation process, so there will be exchange of electrons and maybe some hybridization can happen. So how these uh, things happen in an atomic scale, so that actually is being investigated by mostly uh, this theoretical modeling, so known as a DFT, so density functional theory, where you can calculate uh, the band structure and how this is going to affect the chemistry or the catalysis of your fuel particles or fuel or gas on different surfaces. That is also actively being researched. Okay, so any question on this? Uh, there is some. What is the temperature at which the whiskers are grown? What basically whiskers are doing to electrode? Does the cost reduce after growing whiskers? I'm so in the paper I have to check what is the exact growth conditions for the whiskers. Uh, but definitely the role of the whiskers are again, this is a structure nanostructuring. It is not really actively playing a role in the catalysis. Uh, and whiskers are doing to the, yeah, so they are basically like a support for the electrode, the material which you want to deposit or which is going to act as your catalyst. So for example in here this platinum, cobalt, manganese, which, let me just, so this platinum, cobalt, manganese is coated on this whisker. This is a particular, like, whisker is like this name for this particular morphology. This uh, these structures which are like growing like this, okay, random structures. And uh, but the catalysis is actually done by the active material, which is your platinum based alloy, okay. The cost is reduced definitely, and that is why I mean, compared to any other nanostructured materials, the cost is uh, reduced. And moreover, it is a reproducible way, because you are creating these microstructures, and these whiskers, as you can see, is uh, definitely they are not really I mean, why it is a industrial, it has potential for industries, because there is not much chemistry involved here. Okay, so in other synthesis of nanoparticle or nanowires, so a lot of chemistry is involved. And in this process, so what happens, for example, when you are synthesizing like these hollow spheres, so you use various chemical reagents, and sometimes many of these chemical reagents can stick to the surfaces, okay. And if they do that, so although you think you have created a pure nanoparticle system with, let's say, a platinum, maybe an alloy of platinum or cobalt, but there can be many other chemical reagents which stick or stay on the surface. And that is why this question is always about the reproducibility is always there, okay. And when we talk about the surfaces which are active sites for absorbing hydrogen or oxygen, so they can also absorb other chemical agents or impurities that is present during the synthesis process. And that is why these chemical processes are not that reproducible. But here, this is being done in a sputtering system, which is a physical vapor deposition technique. And therefore, so once you grow these whiskers, and then you coat it with your active catalysis material, so which is grown like a physical way. So therefore, uh, you can do it quite reproducibly, as well as you can do it on a large scale. So you can take a substrate material and deposit these catalysts, and then just make them into a electrode material by cutting some pieces out of it, and then it is ready to go. And therefore, this has like uh, the best, or so far quite promising uh, for going from the lab to real applications. Okay, so in that context, it is like, yeah, one of the successful way where uh, nanostructuring can help. I mean, these are all ideas or strategies still. Okay, so they are not really already used in the real scale application yet. But this is another, instead of this using chemical techniques, so this is a physical vapor deposition technique which might help. So I will share the research paper, this paper which uh, like, from which I have taken all this material, so you can read. And in that paper, so I think that is not a paper, rather it's like a book chapter, which uh, which has many references. Basically, they have compiled all the different uh, nanostructuring that has been done in the field of fuel cell, or that can be used for fuel cell applications. Uh, I mean, I only compiled or presented few of those examples, But if you want to really go into the details, you can, I will share that so you can have a look.